Happy Sunday. This is PFG Live, the podcast that asks if you're not flat, at least you could be dry. Welcome aboard. We got a good group. We've been having some fun in the Discord. Let's start with the YouTube guys. CJ Stevens, thank you for your check, recheck, double check on the YouTube. We have Warren Jones in Sutton, New Hampshire, my neighbor to the north, who reports sunny and in the 70s and bloody nice outside. Thank you, Warren. Awesome having you here. Quentin is reporting from about 30 kilometers north of Ampere, the Netherlands. EHKD, Echo Hotel Kilo Delta, says it's 320 at 3 knots. No significant weather. Broken at 3,300. Temperature 14, dew point 11. Did you hear what I said, folks? Temperature 14, dew point 11. That's important. We'll talk more about that later. And the altimeter is something I can't read. Evils has a whole bunch of things in a format that I can't decode, but basically it's 22.6 science. Dale in Edmonton, Alberta says it's 12 degrees science, 53 degrees Fahrenheit, and cloudy in the country without a postal service. I don't even know. Near the White Plains, DBX is reporting that winds are variable at 4 knots, visibility 10 miles, few clouds at 5,000, temperature 26, dew point 17, altimeter 3006. Josh says audio check. Thank you very much. In southern Manitoba, the METAR is saying it's 150 at 6 knots, temperature 24, dew point 11. The remarks are unimportant. Tuck in Buffalo, New York says it's 77 degrees Frankenstein and sunny in Avengers Tower, which, by the way, is in Buffalo. If you ever get a chance, you should go visit. It's the real one. That's correct. Derv Neutron. I don't even know where to start. 81 degrees Fahrenheit and sunny, starting to get some color in the foliage in Hartford, Connecticut. My neighbor to the south. Yes, we're starting to make fall happen here, and it is pretty nice. So welcome aboard. It is a beautiful day. Here in the Wyndham, New Hampshire, it's allegedly 80 degrees Fahrenheit, 56% relative humidity. At Manchester Airport, they are reporting winds are 270 at 9 knots, visibility 10 miles, few clouds at 6,000, few clouds at 25,000, temperature 29er, dew point 12, altimeter 2996. The remarks are unimportant. Welcome. Nice to have you all. It's been an interesting week. I was deep, and I mean deep, in the hole of designing this thing, which I had to get to a certain point, which I almost finished it. I didn't quite finish it, but it's being tested without one key component. We'll talk about that in a few minutes. So we're going to do two things today. We're going to talk about the physics of moisture in shop air, right? Which is just physics. And we're going to talk about that. And once we get that down, we're going to go back to some of the practical things that we're doing here to measure and control the humidity in our shop air. And the reason we're doing that, the original reason we're doing that, was for 3D printing, right? So dry filament prints perfectly, and wet filament does not. So we have these things called AMSs, which is the filament feeding system that sits on top of the bamboo printers, which lots of us have, although you can have any printer and have a system with a bunch of spools. And generally, those systems keep the spools inside of an environment which allegedly, keeps them dry. And some of them have heaters in them. And we've been using desiccants for a couple of years and measuring what's going on with the desiccants. Evil says, I keep my spools outside the environment. Is this like in a pocket universe? I mean, I don't... Which, I'm not judging you. Pocket universes could be very dry. So we have been very interested in finding things that work. we found a lot of things that don't work. When we first started the what we call the quest for dry filament, I designed this little, what I call the feather workstation, right? And we did a video on this, and we did, there's a bunch of stuff on the website. If you go to pfg.gg/links and you scroll around, you'll find the quest for dry filament, and we'll talk about these feather boards. But in the middle there, you'll see there's a hygrometer, a little Sensirion board, the SHT45 board from Adafruit, a lithium-ion battery from Adafruit. Oh, look, it just took a reading. And the feather board is the ESP32-S3 with the reverse TFT screen. Just means it's on the bottom of the board. And these have been very useful little tools in taking measurements and telling us how we're doing and helping us learn about software and all of that stuff. Before we had those, we had crappy hygrometers, the little round ones, which cost $3 to $5 on Amazon, and it took us a while to figure out that they were absolute junk at the low humidity levels that we cared about. So we might as well talk a little bit, just briefly touch on why, because those things measured the resistance between two electrodes with some sort of polymer coating. And as the humidity went up, moisture would go into the polymer coating and increase the conductivity between two electrodes. So by definition, you're making a measurement of something that's generally going to be a very high resistance. So you're measuring a little teeny current. And they were optimized for in the neighborhood of 50% relative humidity. Well, when we get down to the relative humidities that we like, down in the single digits or so, they're trying to measure insanely small currents, which they can't do. They just can't do it. So they get into, they get a limit. In fact, some of them, the ones I was getting for $3, $4, $5, they would not read below 10%. And at 10%, they were inaccurate. So I literally have thrown all of those out. We went to the Sensirion sensor. I found out that Sensirion made an eval board for, I think, $30, and we were able to buy the Sensirion eval boards on DigiKey. I designed up this nice little housing for them, and it makes it a very nice little package. That's all on my website, by the way. We still have them. And it makes for a very accurate measurement. Why? Because Sensirion took a different approach. They took two parallel plates with a little special spooge in between the parallel plates, and they measure the capacitance of those plates. And that capacitance goes up as moisture goes into the spooge, and it goes down as moisture leaves the spooge. And you might say, well, that's not any different than measuring resistance. You're just measuring capacitance. Well, it is very different, because what they do is they make an oscillator using the capacitor as one of the elements, or as the main element of the capacitance, and maybe a resistor or a current source as another element. And that is able to very cleanly go down to 0% relative humidity and very cleanly go up to high values. So it is a very, very good sensor at low values. I was reading the Sensirion data sheet, which I don't have handy for you, but the Sensirion data sheet calls the SHT45 a 1% sensor. Well, that's amazingly good, and it's way good for our applications, right? So, but there's some things we've learned about these sensors, which I'll get into. Another candidate for an off-the-shelf hygrometer, and we'll talk about why this is important, was brought to my attention by Mr. Doug Chin. This is a Yo-Link. It's on Amazon. Easy to buy. This is $18, más o menos. I bought several of them. I might actually have a couple of unopened packages that are going to somebody who is a close personal friend. But I do have 2 of them live and running right now. These Yo-Links, there's a small one and a big one. This is the small one. They're about $18. Okay, they have a sensor in them from Sensirion. Now, it is not the top of the line Sensirion. Yes, Wesley, I have a payroll. Where's my soundbite for Wesley? Shut up, Wesley. Okay, moving on. I need that. DBX, could you? Yeah, thanks. So, I don't know if I could do this, if I could pull this off live. Yeah, I have a couple of friends. I pay them. So, the sensor in the Yo-Link is a Sensirion sensor, but it's not the Sensirion sensor, the original, you might say. Anybody want to tell me where that came from? So here's a picture of what's inside the Yo-Link. And my buddy Doug sent me this picture, and of course the sensor in question is right there. You see that little guy there? That little package? That is a Sensirion sensor. Not the top of the line one. I'll point a couple of things, but right in my face, as if it wouldn't notice, is this 900 megahertz wire antenna that they paid 27 cents for, and it just, yeah, that makes me a little crazy. But we'll talk more about that in another channel. So there's your Sensirion right there. It works well. I have tested these Yo-Links. They do a good job. Now, when you get into the really fancy Sensirion sensors, they tell you to put them on a piece of PC board with a cutout around it, so there's no stress on the chip. This doesn't have that, and that's just another artifact of it not being the top of the line sensor, which is fine. But that's what's inside those boxes. So we did have a look-see, and we did test them out, and I did put them next to the feather boards, and they work quite well. So that if you said to me, hey, I want to just get something real quick that's accurate, I can't give you a $5 solution, but I can give you like an $18 solution, and that's a pretty good deal. And yes, it's cheaper. It's cheaper than the Sensirion eval board that I carry for this purpose. But the eval board does have the top of the line sensor in it. Okay, so you pick your poison. This is about $30. This is about $18. But neither of them. Now the eval board does talk Bluetooth to a little app that they have, but that's all. It can't go on the network, and so that's something to know about that. So. I think I'm going to flip around our topics. I'm going to keep on the instrumentation side, and then we'll get to the physics later. Okay, is that okay with everybody? Wesley, you okay with that? I don't want to upset you. Yeah, Dave Schaller says move to Tucson. We have a buddy, Protium Machining, who is in Tucson, and it's very dry there. Okay, so time passes, and we're monitoring relative humidity in our various AMSs manually. Okay, so we have a new entrant here. Test Room 2003 is with us. He says, good evening. A little late again. Sorry. It's okay. And he says, hi from Oostkappelle, Netherlands. Welcome aboard, sir. He says, it's 13 degrees science, 71% relative humidity. a little moist, but we'll dry you out, I promise. So we graduated to decent sensors. That was the Sensorion board, right? And then we started drying our filament. All filament that comes in gets dried. And we discovered the aluminized Mylar bags as being the primo bags for storage. And then we started filling the inside of our spools with desiccant. We started doing as much desiccant as we can. But it became a full-time job, as I talked about last week. And you'd run around and look at the Sensorion boards and say, oh, this one needs new desiccant, and then you'd swap out the desiccant. And then when you had enough desiccant, the desiccant would go in the oven, and you would dry out the desiccant. It was a job I wished to leave. I wanted to quit. So we started looking at ways around that. About a year ago, Mr. Chen and I were talking, probably over sushi, and he said, how dry is your shop air? And I said, I don't know. So we measured our shop air, and it was, at the time, I measured 8%. Now I would say it's 7%. And that started this whole LowFlow thing, where we're feeding a very small flow of very dry air from our system and going into the desiccants. Going into the AMSs. So, did you actually grab something? I'll have to look, DBX. So, the things that were missing were, we wanted to get onto a system where we could monitor the relative humidities of things remotely. That took us back to our feather boards. So our feather boards were able to talk to things, and we had them talking to Adafruit.io, which will take data from your sensors and generate graphs and things. But I was going to pay $10 a month for that, and I wanted to pull that inside. And the second place we were publishing to is something called notify.sh, which was a server that did the same thing. It took data and put it in logs for you, et cetera, and then I was paying a couple of shekels for that. So I said, no, I want to bring this in. And somebody introduced me to Home Assistant. We talked about that last week, I think. For sure, we talked about it last week. And Home Assistant was a really good answer. So we wrote some software and replaced the software on the Feather with software, or at least the subroutine for pushing data to Home Assistant, and that worked great. And I posted to the world the first success. Well, now Home Assistant is rocking. Okay, and we have a bunch of sensors on it, and as you can see, I have 6 different sensors on there right now. They're all reporting the charge of the battery. And you can see there's 2 batteries that are very low that have to get charged. There are the readings for the relative humidity and the temperature. So that's been working great. However, you can't stick the featherboard into an AMS with 4 spools in it. You can put a Sensorion board in there, but you don't have the Sensorion board on the network. Thus started this project where I needed all of the above. So I came up with a form factor that fit into the AMS, okay, and it drops in between the 2 feed motors on the front of the AMS. Another benefit is you could look through the front plastic of the AMS and read the identifier, or maybe some LEDs or whatever. And that was what we landed on for the size. And then I started designing the guts. Well, the guts were non-trivial, and we went really far along. I think we're at P8 on the plastics, and I will show you an example of what it looks like inside. So inside we have our feather board. We have our SHT45 Sensorion board. All of this, by the way, is from Adafruit. Hashtag not sponsored, but I love these guys. And then we're using a battery, which is an 18650 lithium polymer battery. And the really nice thing about the battery from Adafruit is they have a version of it that has a protection circuit on top of it, and it has a cable, and it has the standard connector. Right now it's not plugged in because I don't want this running, but it has their standard power connector, and it goes right into the feather board. Very nice battery. This one is labeled as 2200 milliampere hours, and I got to tell you, I have a feather board in the basement that's been running on these batteries, and it's at least 6 months. Okay, in doing what we do. On the old software, I had it going about 6 months on a battery, which is pretty nice. And then all you have to do is yoink it out and plug the USB-C in, and it'll charge right up. So on the bottom of the case, there's the USB-C that goes into the feather board, and just plug that into a 5-volt source, and it charges the battery. The feather board has battery management hardware on it, and software, of course. It's in the software, but it's lovely. So there's your major components, okay? Feather board, temperature, humidity sensor, battery, and then the case design does a bunch of very subtle things. Well, not so subtle is how many holes there are in and around the sensor. And if you look at the commercial products, such as, well, when I first did the Sensorion eval board, you can see that I put holes in the front and the back, right over and under the sensor, right, to give it maximum exposure. If you look at the Yolink, has a bunch of holes on the back of their board, okay, and also on the side of the case and the side of the case, although only the top ones are actual holes. Yeah, they tried, but I think they could be a little more open, but it works. So more open is better to get to the sensor. What else is cool about this? Not shown is a feature which is in development right now, and I don't have one handy to show you, but if you look really closely at the plastics, you'll notice this little widget right there. There's a little feature there, and we're putting a fan in this unit. So when this thing goes to take a reading, it's going to spend some time mixing the air wherever it's taking its reading. So let me tell you about where that feature came from. I noticed if I had 3 sensors sitting on my desk here. Okay, I had the Yolink, the Feather, and the Sensorion eval board. And I wanted to see if they would match. So they were sitting in my office, so I could look at them right around the corner here. And what was really bugging me is that they were never the same. Did you ever hear the saying, man with 2 watches never knows the correct time? That's what was going on. I'm like, what's going on here? So I took the units out to the bench in the electronics lab, and I had a little fan, and I just ran a fan over them. And it was like 15 seconds. They had all gone, broop, and they all locked up, and they were all within, tenths of each other. And I'm like, okay, message received. So we had started thinking about the fan idea, and then this was like confirmation that this is a good idea. I don't have data to share with you yet because I'm waiting for some more parts. Adafruit, I placed an order a couple of days ago. I've got a bunch of feather boards coming, and I've got a bunch of power converters coming, which are needed to run the fan. Long story. but there'll be a little more development on this thing before it is what I call complete. And then there's a little bit of software hacking to do the right thing. So that's coming, and it's very exciting. So stay tuned, and we will give you more updates. Let me just see, what was the P number on this? Yeah, this is at P8, and P8 is pretty solid. So just stay tuned. And if you're on the Discord server, in our 3D printing channel, there is a thread that I started on the LowFlow air system. And in that thread, I'm posting updates on the new KP hygrometer, and we'll keep posted on that. But it's designed to work with Home Assistant. So each one of those hygrometers, and the first two that are actually operational but without the fan, are these two guys here, the bottom 2 rows of this chart. And you'll note that one's at 14.9% and one's at 14.8%. The system is currently programmed to servo between 13% and 15%. And those are good numbers. Those are numbers that make us very happy when it comes to dry filament. You could get them lower. If you're not using exotics, you won't appreciate a lower number. The manufacturer says 20%. If you dig deep enough, you'll find that number. So I did a couple things. I turned the airflow up. So it was 5 psi behind an orifice that was 10 thousandths in diameter, feeding each unit. I just turned it back up to 10 psi behind a 10 thousandths orifice feeding each unit. But now we have a servo, so it'll turn off the system when everybody is dry enough. But if anybody is not dry enough, it'll turn on the system. And that's working out, I think, pretty good. One of the challenges with all of this is that the time constants associated with it are very long. This is not a fast bang, bang thing. This is, okay, now you've made a change, and now it's going to take a couple of hours to evaluate that change. So I can't tell you immediately if everything's working, but we saw the first signs that our closed loop servo is functioning. That's done inside of Home Assistant. So once your sensors are in Home Assistant, you could make what they call automations. And you could say, if this sensor and that sensor, blah, 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 then do these actions, including sending notifications to you. So like if you could set up a thing that says, if my humidity readings go above 22%, immediately send me a message like something's wrong. So that's all possible inside of Home Assistant. So, very happy with how that's going. So just a reminder that moisture diffuses through plastic. We've proven that. When we were looking at different containers, we absolutely proved that moisture marches right through the plastic. We did research on it. We found research papers that says moisture goes right through the plastic. And then we found our favorite Mylar, aluminized Mylar bags. And it's the aluminum, the metal and glass that will stop the moisture. So an AMS is made of plastic. Your spools are made of plastic. Your plastic is made of plastic. Just keep that in mind. So the airflow that's continuous is got a continuous job to do. But also the tubes leading from the manifold to the unit are made of plastic. And one of the questions that's lingering is, does that matter? And I would argue that if this was a PhD thesis, we would go after that. But I believe we could hit the numbers we want to hit without heading down that road. I mean, we're really super close to calling it accomplished, mission accomplished. Put the banner up. But we'll see. There was a theory that you get stratification inside a closed volume. And I think Robin used the term puddling. You can get these wet areas. So I did a little research on that, just research, not a lot of experimentation. And it supports, the fact that we're going to mix the air with the fan is part of the whole idea of overcoming that, both from a measurement standpoint and from mixing up the volume that it's enclosed in. So that's a good thing. But the literature didn't support it. I couldn't find anything that said humidity will stratify. Now, temperatures can stratify because of convection. Temperatures can stratify because the floor is cold and the ceiling is warm. And temperature is part of the calculation that gives you relative humidity. So you could make the argument that that's part of it. But we're going to hopefully obviate the argument by mixing the air. And that's what we're about to do. So if the creek don't rise and the good Lord willing, next Sunday I will have a unit that is like the final vision of having the fan in it. And right now the notional algorithm is measure infrequently for battery life. When it's time to make a measurement, perhaps once an hour, you come up, you turn on the fan for a period of time, let's say 1 full minute, you run the fan, and then you take your measurement. We know that the Sensorion sensors have a time constant that's actually really good. So this sounds about right. So you run the fan for a minute, you take a measurement, you post your measurement to the server, you do anything else you have to do, and you shut down and you go back into low, ultra low power mode. If you don't need to do anything for 2 hours, you set it to 2 hours, right? You'll have some knobs to turn. And that will allow that 18650 battery to last a very long time. I do have data on the fans, how much current they take, and I will be able to do some calculations as to, what the trade-offs are. So that's a little bit on that. I wonder if, and you notice that when we we do it for fun, but when we do the aviation reports, that there's a temperature and a dew point. Because in aviation, we watch the delta between the dew point and the temperature because we care about that. A cloud forms when the dew point and the temperature become equal. Okay? In other words, droplets form when that happens. Water does a phase transition from water vapor, which is a gas. You could fight me on this, I know, to water droplets, which is a liquid. And that happens at the dew point. So when your temperature comes down and hits the dew point, that's when that happens. So that's why we care about dew point in aviation, and we talk about it all the time. But that's what dew point is. Relative humidity is a calculation off of temperature and dew point. It is what percentage of how much water is the air capable of holding, and how much water is it holding. So if you're at 50% relative humidity, which is sort of the shirt sleeve, wonderful, perfect setup, that means there's water vapor in the air, and it's about half of what it could be holding. If you go to Tucson, Arizona, and you go visit, he's not here with us today, you go visit Protium, you're gonna really quickly notice that the water vapor in the air is a lot lower than what it could be, and therefore the humidity is low. Dale says, or come north in the winter. So Dale's in Edmonton, Alberta, where it is also very dry, especially in the winter. Same thing. And then there's some places where in the UK, London fog. Why? Because the temperature and the dew point are hitting each other and it makes fog. Dave says, wrap all the tubes with aluminum foil or pressurize the AMS so there is a small airflow down the tubes. So that's what we're doing. We do have an airflow down the tubes. And at 10 psi and at 10,000ths orifice, I have proven that there's insufficient pressure buildup in the AMS to hurt anything, but enough to push out the air that's in there. And we have done experiments with aluminum tape, and that does have potential. But again, if we can make this thing work with the simple stuff where it meets engineering requirements, and I would say 15% relative humidity without thinking about it is meeting engineering requirements, I think that's what we're going to do. Okay. Let's see. So I wanted to show you this graph, and then we're going to get back to this, but I think it's an important graph to show you. This is how you define dew point. So, I'm sorry, this is how you define relative humidity with respect to dew point and temperature. So if you look at this graph, right, we have a bunch of lines. The lines represent relative humidities. So let's just pick an air temperature. We'll just say this is, of course, Fahrenheit for air temperature. We'll use this line here, right? 58 degrees. Oh, here it is. 15. No, we'll use 20. 20 degrees Celsius, right? So at 20 degrees Celsius and a dew point of 20 degrees Celsius, that's where that line is. If we that's 100% relative humidity. If we go to 50% relative humidity at standard temperature, that's a dew point of about 9 or so degrees C. So if we were in that environment and we went to a refrigerator and we opened the door of a refrigerator that was at or below 9 degrees C, you would get condensation on the inside of that door because you just lowered the temperature. Robin just asked a question. Robin says, is there a gravity-induced gradient from the higher humidity being more dense? If so, would there be a benefit in having the dry air enter the bottom of the AMS, possibly move the orifices to multiple at the AMS bottom? So, yeah, so Evils makes the argument that dry air is heavier, but it's not a bad thing to consider, Robin. I specifically went to the literature looking for evidence that somebody had, that this happens, and I had actually counter evidence, and the counter evidence was you get stratification due to temperature in air, but you don't get stratification in the relative humidity. So let me clarify that. The relative humidity change could be due to the temperature stratification, which I don't think helps us quite yet or matters. We'll find out. So there's the graph. That's the definition of actual relative humidity as it pertains to dew point and air temperature. We've been trying to shoot for, this red line down here is 20% relative humidity. It's actually below their chart, so we can't quite get there. But if we use the next one up, which is 30% relative humidity, which is, ungodly moist for what we're trying to get at, that dew point is around 2 degrees C. So at standard pressure, you would have to be about 2 degrees C to condense out the moisture that is in 30% relative humidity air at 20 degrees C. Okay, you'd have to drop. You'd have to drop. You'd have to have a difference between air temperature at 20 degrees and some object at 9 degrees to get condensation. Yeah, Rommel says it will take a very tall AMS for this effect of height and humidity to kick in. It feels. I have to agree. So let me show you a short video. I get a I'll show you where this came from. We did get a message from one of our viewers. Listen, guys, it's okay to use your real name. Like, actually, on the server, we prefer you use a real name, or at least a first name, so we know how to relate. I recognize that some people like to preserve some anonymity, and I'm okay with that. I really am. But, maybe back channel to me and say, hey, this is who I am. It helps. This came from a guy, his handle is Lathe Lover 43701. I don't know who you are, Lathe Lover 43701, but I get this message. He says, as usual, enjoyed the PFG.Live. If you're willing to take a topic request, recommendations for checking moisture levels in a shop compressed air system. Ideally, less expensive, $100, $200, easy to use. For example, plug in a line with a blow-off gun, something like that. He says, I respectfully disagree that shop air is dry. Many shops suffer from no dryer, high humidity levels, don't drain tanks, poor system design, etc. And shop air can be very wet. Signed, Lathe Lover 43701. Well, Lathe Lover, we're going to take care of you. Josh says it sounds like a John. Probably a John. I'm not judging. And Evil says most Johns do prefer anonymity. Well, that is true. So let's put up this slide here, and this is a video. I'm gonna run the video. I think we have this technology. Hope this works. I don't think the audio is coming through, but as you can see, we're just using a plastic bag and the Yo-Link sensor. Oh, Evil's hears it? Okay. Watch the numbers. Okay. So that was a pretty good demo. So lathe lover 43701. It's John. Okay, it's John. So John asked for an inexpensive way to check shop air. It doesn't get better than this. Okay, that was an $18 sensor. It was an air gun, and it was a couple of minutes of time. But you can imagine making a container. So I actually made another one of my reference jars today and put my test unit in it. And that's a good example of this sensor sitting on John's shop air system would tie right into Home Assistant and give a continuous reading of the shop air humidity. You'd need the an orifice and possibly a regulator to get the pressure down to make a tiny bleed air. But we do know that 10 pounds in front of a 10,000th orifice would do a really nice job, and this would feed right into Home Assistant, generate alerts, and be part of the team. So there you go, lathe lover 43701. I think we gave you a continuous monitoring system for under $100. Of course, I haven't told you how much it's going to cost you to get one of these. It might not be under 100. Okay, so that answers now. And John was the trigger for this topic today, because I think it's pretty important. Now, there's a big difference between shop air in a production environment and shop air in a small guy environment. Okay. Tim Beattie says shop air almost by definition is drier than ambient. You are correct, and we'll talk about why in a second. John will argue, but we'll get there. Hang in. And he says that same mechanics as heating air in the house in winter will be drier than outdoor air. Sure. Does anybody here get dry skin, bloody noses in the winter because it's so dry? In your heated house here in New England? Right. So the difference, when small guys with small air demands talk about, having an air dryer and getting really 8% dry air, look at me, woohoo. It's a lot different than somebody who's got, 6 machining centers running and, 2 compressors, etc. And we're going to talk a little bit about why. Okay. So let's get into the physics of this stuff and explain what the heck is going on. We're going to start with what's called the ideal gas law. And the ideal gas law says, I'm going to use this is the old technology. The ideal gas law says PV equals nRT. Okay, there's more to the story. I get this comment on YouTube. You go to the YouTube thing and you say, "Oh, you have a comment on your video," and I read the comment before I read figure out which video it refers to, and the guy says, "It's pretty useless if you hold something up that's mirrored. Your phone is mirrored, so you can't read that. That's really just totally useless." And it turns out he was commenting on a 3-year-old video with me and Stefan Gottsventer on the PFG.Live that we started doing in the shop from my iPhone, and it was mirrored. Remember that? So I just did this to piss that guy off. Okay, that's all. You got to have a little bit of fun. Okay, so PV equals nRT. So what does this mean? I want you to memorize that because I'm going to put it down. Okay. Pressure times volume equals the number of atoms, okay, it's actually the number of moles, which is just a multiplier, okay, times a constant, R, don't worry about that, we're not even going to talk about that, times temperature, Kelvin, absolute temperature, okay? So if PV equals, can I put that right there? Oh, look at that. If PV equals nRT, then I'm going to ask you a question. If I raise the pressure, what happens to the temperature? Temperature goes up. Okay? If I raise the temperature, what happens to the pressure? Pressure goes up. If I lower the volume, well, let's put it a different way. If I lower the pressure, what happens to the temperature? It goes down. If I lower the pressure fast, what happens to the temperature? It goes down fast. Okay? So this is called the ideal gas law. And if you've ever grab your air gun in the shop, put your hand on top of the air gun, feel what the temperature is, and then blast it, for 15 seconds and feel what the temperature does in your air gun, it gets cold, right? And this describes what happens to gases. Also, if you go to, I go to Air Gas every week to pick up raw materials to make PFG stones, which reminds me, if you need some PFG stones, you could head on over to PFGstones.com and pick yourself up some really flat, wonderful goodness to help you in your precision shop. PFG stones, they're not just for breakfast anymore. And big thanks to Mr. DBX who made our next sticker, which I'm still chuckling about. That's an actual shipping sticker, but I digress. So I go to Air Gas and I hear them loading up cylinders with gas in the back. They have a whole, it's a commercial operation. And I know a lot of times they have to put the tanks in a cold water bath to handle the heat generated by compressing the gas into the cylinder very quickly. So they are forcibly lowering the volume, raising the pressure a lot, okay? And the result of that is temperature goes up. So they have to get the temperature out of there. Now, here's a question for you. When you go buy your tank or pick up your tank or trade your tank at Air Gas and you get 3,000 PSI in that tank, what pressure did they stop filling it at? 3,000 PSI? Higher or lower? Dale knows. I know you're typing, Dale. Dale's an expert. And the answer is, everybody's typing. We'll give you a moment. Evil says, is that why I got more than 200 bar on my argon? They filled it on a cold day. You're not wrong. So it is highly likely that they have to fill it higher than the target number. Yeah, there we go. Test room knows. He says it's higher. Correct. They have to go higher than the target pressure because then it's going to cool off and it's going to come back. So there's some science happening at your gas supplier to deal with the ideal gas law. Okay? Unless it's a CO2 bottle. Hang on. Don't get ahead of me, Dale. Jeez. I love smart people. And I hate smart people. Okay. So here's the here's the problem. Moist air, and the problem we're dealing with moisture in our air is not an ideal gas. If you're going to buy dry nitrogen, more power to you. But water vapor that we're trying to get out of our air is not an ideal gas problem. So this gets you some of the way to understanding how pressure and temperature and volume and all that stuff works, okay? But it's not our problem. Our problem is as follows. Let's take a cubic foot of shop air, okay? You could all imagine a cubic foot of shop air, and let's follow it through your shop air system, and let's see what's going on, and we could add some color commentary. First, we're going to take in the air. So it's 70 degrees Fahrenheit or 21 degrees C, and it's 60% relative humidity. Pretty typical day. 1 cubic foot of air is going to hold about 0.1 fluid ounces or 0.3 milliliters of water vapor. You can't see it. It's there. It's not hurting anything. Now, we suck that into our compressor and we take that cubic foot and we compress it. Here's where the action starts. The compressor grabs the air and squeezes it to, let's say, 120 psi or 8 bar. Okay. In the process of compressing it, what do we know? Which way does the temperature go? It goes up. In fact, that process will take that air up to 200 to 300 degrees Fahrenheit, 93 to 150 degrees Celsius. Okay. Just from the compression. Hot air holds more vapor, so at this point, all of the water is still vaporized. This is an important point. You started with room temperature air, you compressed it, okay? It went up to 300 degrees Fahrenheit, and it's still water vapor and air, okay? It's still got moisture in it. Nothing changed except it's compressed. Under light loads, okay, the discharge isn't going to be as hot. Some vapor might begin condensing. Under heavy loads, the compressor stays hot and the water vapor stays vapor. So in a factory situation where the compressor's hot, the tank's hot, everything's hot, the water vapor is still water vapor. But now it goes into the receiving tank or the storage tank. You guys would have different names for it. I have an 80-gallon. I'm not judging. It goes into the tank, and maybe it gets to it cools down to about 100 degrees Fahrenheit. It's warm, right? But you know what's going to happen. It's going to hit the dew point at that pressure, at that temperature, and it's going to start condensing in the tank. Has anybody here ever had water in their compressor tank? That's the condensation, which takes time to happen, okay? So if you're a lightly loaded system, yeah, Dale says no because I have auto drains. Of course you do. And Evil says, I've never seen water in a compressor tank. That very serious guy. So a simple compressor and tank will accumulate water in it under light load conditions, like a small shop, a one-man operation, a hobbyist, even an R&D shop. You're going to accumulate water in the tank. Now you go to use some of the air. What's the relative humidity of that air that you're using in the shop versus the air that went in? It's drier because the water dropped out of it. Okay? So that's all very simple until, John calls you up and waves his fist in the air and says, wait a minute. Wet shop air is a problem. It's a problem if you're using a high volume of air, because now you compress the air. It doesn't have time to drop out in the tank. It gets thrown right into service. It gets blown down the distribution lines, and it condenses where? Where does it condense? In the distribution lines. So now a properly designed system is going to have traps, in the distribution lines. But if you're blasting air through this thing, you don't have time to condense, and then it gets into your machine and it condenses there. Or it condensed just before it got there and you blowing water into the machine. This is what makes people unhappy. And this is why Lathe Lover 43701 was unhappy. Okay. That's without a dryer installed. So now you say, oh, I'm smart. I'm wicked smart. I'm going to put an air dryer in. What does an air dryer do? The most common air dryer is going to be a refrigerating air dryer. In other words, you're going to blast the thing into a heat exchanger that's going to cool the air from that 100 degrees down to something cold. Mine goes down to 40 or 50 degrees Fahrenheit. It's not crazy cold. It's cold. It's like refrigerator cold, okay? But it's at high pressure. It condenses the liquid and it drops out and it shoots that liquid over to a tank or a drain on my system, which is in our is in our thumbnail. You can see I have a 5-gallon container, water cooler container, and it goes there, and it fills up relatively slowly. So the refrigerated dryer lowers the air temperature to, it says here, 35 to 40 degrees Fahrenheit, which is fine. Leaving most of the vapor behind as liquid. Dew point is stabilized at around 35 degrees Fahrenheit. A desiccant dryer, if you really have to get it dry, will take it even further down. But now you're dealing with desiccant maintenance. And then there's all sorts of fancy machines to dry the air out there. So, when it gets to the tool, this is why you have to consider the volume of air in use. And I am, when it comes to air systems,
I am not an expert.
But I will tell you this. You have to consider the volume and the rate of usage of the air, because if you're using a lot of air, the system doesn't have a chance to dry it. And that's the disconnect between why I can say, oh, look at my 8% air. It's wonderful. And John yelling at me, but yeah, we got all this stuff and we're getting wet air. This is the why. So, one of the things that John wanted was a way to continuously monitor the air moisture content in the shop. And so my proposal, and we'll figure out a way to make this happen, is, go to the end of your distribution system, or the far side of your distribution system, hang one of these, one of these magic jars that look like, oops. Why am I getting an exclamation point there? But anyway, you basically hang a jar of tomato sauce that's been modified. And you make a continuous measurement. Dale says it turns air guns into water guns. Yeah. He says industrial desiccant dryers are self-regenerating. The 2 tower types. Yeah. So there's a type. Oh, thanks. Nice graphic. There's a type of system where you have a bunch of desiccant and a bunch of desiccant. And while you're using side A, you're drying side B. And then when side A gets saturated, or based on a timer, they swap. So you're basically pumping energy in and getting the drying from the desiccant. And that brings in, that can bring you in for a landing at a much lower moisture content than perhaps a refrigerated dryer can. For the purposes of what we do, 3D printing, normal machining, normal stuff. If we had 8% air, we'd be thrilled. In the AMSs, if we had 15% not with exotic filaments, we'd be thrilled. But there are people that do painting. There are people that do airbrushing. There are people that do some operations that really, really need dry air. That would be the lineup, okay? Compressor, appropriately sized. Refrigerated dryer, appropriately sized. Desiccant dryer, appropriately sized, and then your air would be dry. And you don't have to worry about wet shop air, which I really appreciate. So we're going to take up a collection and see if we can't buy John a jar of Filetto di Pomodoro from Michael's of Brooklyn, which, by the way, is on Avenue R in Brooklyn, and it is a really yummy tomato sauce. And we appreciate them very much. Hashtag not sponsored. So I hope you're starting to understand the physics of what's going on and what we're fighting. If you're in a commercial situation and you have a wet shop air and you bought what the guy told you to buy, you didn't buy the right thing. You need more. You need betterer. Okay? And don't forget, and this is for my buddy who left the comment on YouTube, the ideal gas law is ideal only for ideal gases. Don't ever forget that. Okay. You guys have any questions, comments, or crude remarks? Please put them in the live chat. Otherwise, we're going to bring this guy in for a landing. Give me 20 degrees flaps down, and we'll try to make it to next week and report other good news. Yeah.
Surely you can't be serious.
I am serious. And don't call me Shirley.
Nice seeing you guys. Glad you were here. Hope you understand a little bit more about being less moist. And we're looking forward to next week and showing you an updated KP hygrometer with a mixer and some performance numbers. In the meantime, I have to get the slide up because it's magnificent. There we go. Get flat. Stay flat. And we'll see you guys next week. Take care.